Hi everybody, and thanks for listening to this talk. In this study, my co-author Robert Viesca and I had a look at how aseismic fault slip nucleates and arrests during and after fluid pressurization. So we are interested in understanding the coupling between fluids and frictional slip for both natural fluid sources such as metamorphic dehydration reactions, which can be linked to seismicity swarms, slow slip events, or episodic tremors, and for artificial fluid sources with a particular interest towards induced seismicity problems in the context of geoenergy and geostorage application. From observations, both from the laboratory and the fields, we know that aseismic slip drives microseismicity and that it can potentially be seen as a precursor to major seismic events. There is a series of previous studies in the late 90s, early 2000s, which looked at the migration of microseismicity from a purely hydraulic perspective, defining triggering and backfronts as function of the fluid diffusivity. In our work, we tried to shift the focus from a hydraulic perspective to a mechanically driven aseismic slip, and there are several studies led by my co-author and also other collaborators which looked at this approach for constant pressure and constant injection rate injection. In this presentation, I'm gonna present to you how we can extend this approach to have a look at what happens during the depressurization phase, meaning after we stop injection. So to do that, we consider a two-dimensional model with a one-dimensional fault, which is here represented with a dashed line, and we consider injection directly on the fault. We model aseismic slip using a constant friction coefficient, and the main assumptions of this model is that fluid diffusivity is constant and that fluid diffusion only occurs on the fault, meaning that there is no leak-off to the surrounding elastic domain. And finally, we also assume that fluid pressure and the stress field is uniform prior to injection. So we consider the quasi-static stress equilibrium linking a distribution of fault opening epsilon and fault slip delta to distribution of normal stress sigma and shear stress tau. The fluid pressure is governed by a diffusion equation with a fluid diffusivity alpha. And finally, we formulate the fault frictional strength using a constant friction coefficient F, and we rely on the elastoplastic slip decomposition to update the slip at each time on the fault. For that, we consider only zero dilation deformation, meaning that the fault opening is purely elastic and only the slip has a plastic component. So before showing you the results for the depressurization phase, I would like to highlight some properties of the model for the injection case. So here you can see on the left slip profile at 3 different times, so t equals 1 minute, t equals 5 minutes, and t equals 10 minutes after starting injection at a constant pressure. And in black you see the analytical solution developed by my co-author and recently published, and in red our numerical simulations, the numerical solutions. And a particular properties of this system is that if we choose the proper scaling, all these curves can collapse into one, meaning that the slip profiles are self-similar. And if you want to know more about these results, you can have a look at my co-author poster, which is going to be on Tuesday, December 14th. So during this pressurization phase, there are two parameters which are important to introduce. First one is the fault stress parameter, noted capital T, which links the stress criticality and the amount of pressurization that we impose. So this parameter is bounded from 0 to 1 with low value close to 0 corresponding to critically stressed faults and high value close to 1 to marginally pressurized faults. The second one is the amplification factor, which captures the relative position of the rupture front driving aseismic slip to the fluid front. So if this parameter is larger than 1, that means that the rupture front is ahead of the fluid front, and if it's below 1, that means the rupture front is behind. And as you can see here, both the analytical and numerical simulation show that for critically stressed faults, meaning for low value of the parameter T, the rupture front is ahead of the fluid front, and which is in agreement with the recent study. Doing the pressurization, we can also have a look at the shear stress profile, so here in black, and the slip profile in red. And within the slipping region here, which propagates away from the injection point, the shear stress is equals to the shear strength with a constant friction coefficient. And we also have some high value of shear stress at the tip of the slipping region. So to study the depressurization phase, we design our numerical experiments in the following way. So first, we consider a pressurization phase with constant pressure injection for duration Tp, which is a pressurization duration, and after that, we switch off the boundary condition for a system and let the fluid pressure be free to diffuse over time. So here on the left you see the evolution of the maximum pressure over time, and during the pressurization phase is constant and fixed by the boundary condition, and during the depressurization phase it decays over time due to diffusion. And we're interesting to know how aseismic slip evolves in space and time during this phase. So during the depressurization phase, we can still see that there is a rupture front defined the same way as during the injection case, but also there is a locking front which drives the locking of the fault from the injection point, from the previous injection point, which propagates away. So here on the left you see the profile of the fluid pressure in the solid line during the depressurization phase at a given time, and the dashed line corresponds to the profile of the fluid pressure at the end of the injection. So around the previous injection point, we see that the fluid pressure drops because we switch off the boundary condition, and that locks the fault. But far away from the injection point, there is a slight increase of fluid pressure, which then controls the shape of slip rate patches which are still propagating and controlling the rupture. If we have a look at the evolution of the rupture front and the locking front over time, so here in black you see the evolution of the rupture front, and in red of the locking front. I also added in dashed black line the evolution of the rupture front if injection would have continued. And one main result that we can see here is that the rupture front still propagates during the depressurization phase, even if it's at a much slower pace than if injection would have continued. Another important thing that we can notice is that the evolution of the locking front seems to behave in a different way than the evolution of the rupture front during the injection case. So there is a different mechanic which is driving the evolution of the locking front. And finally, we can define the arrest time of aseismic slip as the time when the entire fault is locked, or in other words, when the locking front meets the rupture front. So here you can see the shear stress profile in solid line at a given time during the depressurization phase, and in dashed line at the end of the injection phase. So we see that within the locked region in the center, which increases in size over time, there is a slight increase of shear stress, and within the two actively slipping regions, which are symmetric, we see that there is a stress transfer of shear stress, which is driven by the rupture front, and we still find these high values of shear stress at the propagating tip of the slipping regions. So here on the left you can see the evolution of the maximum slip rate over time, and we investigated the influence of the pressurization time on the slip rate during the depressurization phase. And what we found out is that if we scale the slip rate by the inverse of the square root of the pressurization time, all our results, considering different values of Tp, collapsed into one curve on the left. So the main message here is that the absolute value of slip rate during the depressurization phase are proportional to the inverse of the square root of the pressurization time. And finally, we had a look at the hour's time of aseismic slip as a function of the force stress parameter. So we consider different values of the force stress parameter by varying the initial shear stress acting on the faults. And what we saw is that the hour's time, the force stress parameter has a drastic influence on the hour's time, and more importantly, that the hour's time is proportional to the pressurization duration. And finally, we found out that critically stressed faults, or low value of T, will slip for a drastically longer time than marginally pressurized faults. So to summarize this presentation, during the pressurization phase, we showed that slip profiles are self-similar and that the fault stress parameter controls the relative position of the rupture front with respect to the fluid front, and these two results are in agreement with previous studies. And during the depressurization phase, we found out that the rupture front still propagates even at a slow pace during the depressurization phase, and that the locking front is controlled by the fluid pressure difference, and it propagates away from the previous injection point. Finally, one important result is that hour's time is proportional to the pressurization time, and that critically stressed fault will slip for a drastically longer time than marginally pressurized fault. Thank you for listening to this talk. If you have any question, you can reach me by email, or you can also join the live session which is going to be on Tuesday, December 14th. Thank you.